Good morning, dear colleagues, dear students. Today will be our last seminar in this year related to the different tasks of radioactivity, radiochemistry. And today it will be the overview of everything that we already learned. And so we will go quickly through 8 tasks. And actually, these tasks, they are typical for the control work, so the testing exercises of our students. So we will start with simple the law of natural decay and of radioactive decay, and we will solve quickly this task. We have a rubidium fluoride, and we need to calculate its specific activity. I remember that the term activity means the quantitative property, so it is several becquerels per gram, for example, and the term radioactivity is just a phenomenon. So when we are talking about the quantitative parameter, we should use the term activity. So we know the composition, natural composition of isotopes of rubidium, and we know the half-life of the radioactive isotope of rubidium. So the specific activity, A, it is activity divided by mass in this case. And let's take as a compound we have a rubidium fluoride. Okay. So what is the activity? Activity, due to the law of radioactive decay, is related to the amount of rubidium in this case with this equation, and number of atoms, it is the amount of our matter of our compound multiplied by the Avogadro number, and this amount is equal to mass divided by molar mass. And in our case, as far as the stoichiometry of our compound is 1:1, that means that we don't need any other coefficients. As, for example, if it would be rubidium sulfide, for example, like this, then we should multiply it by 2, yeah? Because we use here the number of atoms of radioactive material of rubidium in our case. But we have rubidium fluoride, so the stoichiometry coefficient is equal to 1, thus we don't need to use any coefficient. So we put this equation in this equation and then put it here, and thus we will obtain that activity is equal to lambda mass divided by molar mass and multiplied by Avogadro number. And thus we're going here, we put our equation for activity here, and we see that the mass will be neglected, and thus it will be simply lambda Avogadro number divided by the molar mass. And lambda, it is logarithm 2 divided by the half-life of rubidium, and here's molar mass. And again, as usual, we put now numbers. It's logarithm 2, 602 10 to 23, divided by, let's take a molar mass. So it is for rubidium fluoride, it is 85 plus 19, so it will be 104. And the half-life, it is in years, but we should convert it to seconds, so it will be days, hours, and seconds. And thus, finally, we will get 2007, let's say, becquerel per gram. So, this is a simple example how we can calculate the activity even of the natural compounds that we take from the lab or from the earth, and we can see that again radioactivity is everywhere. So let's go to the next task. So now we have a decay scheme. So we have a chain of radioactive decay, and in this case we can see, sorry, it's not on English, but here it's 25 days and here it's 75 seconds. And we can see that it is a case of secular equilibrium when we have a half-life of the mother radionuclide much longer, more than 100 times longer than the half-life of the daughter radionuclide. And we can use very simple equations in this case to calculate the accumulation of the daughter radionuclide. In this case, this equation will be that activity of the daughter radionuclide is the initial activity of the parental or mother radionuclide minus exponent or decay of the daughter radionuclide. And we can use it when the daughter radionuclide is still accumulating, and when the equilibrium is reached, then we can use a very simple equation. That means that the activity of these two radionuclides, they are equal, and the activity decreases due to the decrease of the activity of the mother radionuclide. So we have a strontium sample that is purified from all the daughter radionuclides, from rubidium in this case, and we have to calculate the time, the minimum time when the activity of the accumulated rubidium will be 35 megabecquerel. We should calculate activity of rubidium after 50 days and calculate the ratio between this between atoms of these two radionuclides after 65 days, and determine the time when the total activity of the sample will be equal to 25 megabecquerel. So the first task is quite simple. We have already this equation. That means that we can write it like so. The daughter radionuclide will be 35 megabecquerels. The initial activity of mother radionuclide is 50 megabecquerels, and we have to calculate this time from this equation. So we can express it like it is a fraction. That means that exponent will be equal to 1 minus 35 50th, so it will be 0.3, and thus time will be equal to logarithm 0.3 divided by logarithm 2 and multiplied by the half-life of the rubidium. So, And half-life, and in this case we can use seconds, so it's not a problem. So it will be 130 seconds, 0.3 seconds, yeah. So quite fast. This strontium-rubidium relationship is used in the generators for the rubidium-82 for medical applications. So you can see that already after a few minutes the equilibrium will be reached, and we can use this generator again. So the radioactivity of rubidium after 50 days. After 50 days, we can say that the equilibrium is already reached, because we assume that after 10 half-lives of the daughter radionuclides, so I will try to correct it here, so it is 75 seconds, the half-life of rubidium, and 25 days for strontium. Okay, so 10 half-lives of daughter radionuclides. Daughter radionuclide, it means 750 seconds. That is equal to roughly 12.5 minutes. So that means after 50 days the equilibrium will be reached, and we can say that the activity of rubidium will be equal to activity of strontium-82, and thus that means that we should calculate the activity of strontium after 50 days. And we can see also that 50 days it is 2 times of 25 days, and that means that the activity of our strontium after 50 days will be 1/4 of its initial activity. So after 2 half-lives we have 1/4. That means that the activity will be 12.5 megabecquerel. And it will be equal to the activity of our rubidium. So that is the answer, 12.5 megabecquerels. What is the relationship between the number of atoms of strontium and rubidium? Again, after 85 days, it will be still the equilibrium between these two elements. That means that we can write it again. And the activity, it is lambda n, so it is the same. And we can write it like this. And as far as we know that the lambda, it is reverse to the half-life, that means that it will be the reverse relationship between the half-lives. So that means that this ratio will be the follow. So number, here again I am not correct here. Here it should be lambda 2, and here's lambda 1. Okay, and here's lambda 2, lambda 1. Yeah, like this. And now the half-life of our strontium, our mother radionuclide, it is 25 days, and we should convert it to seconds to compare with daughter radionuclide. and divide by the half-life of the daughter radionuclide, so it is 75 seconds. It will be 28,800. So almost 30,000 times more atoms we have in our system, more atoms of strontium-82 we have in our system. Again, you can clearly see that when you have a similar activity, but due to the different half-lives, you will have different amount of the radionuclides. And D is quite simple. When the total activity will be equal to 25 megabecquerels, that means that it is a sum of activity of strontium and rubidium. We know that quite fast these activities will be equal, and thus we have to determine time. Then the activity of each of the radionuclide will be equal to 12.5 megabecquerels. To have in sum 25 megabecquerels. And we already know this time that after 50 days the activity of both strontium and rubidium will be 12.5 megabecquerels. So the answer is 50 days. Okay, let's go to the next task. So this task is very similar, but the conditions are different. In this case, we irradiate our sample with neutrons to produce the radionuclide, and we have to determine the activity of the sample after irradiation. And we remember this, again, not very difficult equation. So it is activity of the radionuclide that is accumulated during the irradiation is equal to the flux of the neutron, the cross-section of nuclear reaction, the number of atoms that are converted to the radionuclide, and this brackets that are very close to the case of secular equilibrium. So we have all the numbers, and let's solve it very fast. So activity of the first sample will be so the flux is equal to 2 to 10 neutrons per square centimeter per second. The cross section of nuclear reaction is 27.2 10 to minus 24 squared centimeter. Number of atoms irradiated. So we have 150 milligrams, so it is 10 to minus 3 grams. Scandium is a mononuclide element, and the mass of this element is 45. Okay. So it is gram per mole. And multiplied by the Avogadro number, so it's 0.2 10 to 23 mole minus 1. And then brackets, so 1 minus exponent minus logarithm 2. And here we don't need to convert the half-life to the seconds, because we have time and half-life in the same units. So we just take half-life of our scandium and multiply it by 30. Let's calculate this first part of the equation, because we will use it again to calculate the activity of a second target, because this part will be similar, not similar, the same. So this part is equal to 109 10 to 9. So seconds minus 1. And now we calculate these brackets. So it is O 22. So it is 2.4 10 to 8 becquerel. Okay. So now the second target, A2. This part we will, so it is the same, we will take it without any changes. But here in brackets, the only difference will be in time of irradiation. Instead of 30 days, we will take 100 days. 6.1 10 to 8 becquerels. Okay, so again it was a rather simple task. Let's go to the next one. So there are two tasks, but they're very close to each other. We will start with the first one. So we know the maximum range of beta radiation from one of the radionuclide, and we have to calculate what is the layer of water will be needed to decrease the parallel this flow of beta particles by 10%. In this case, we can use this attenuation factor that is equal to exponent minus mu d, and we know this maximum range, and we can use we need to know the radiation factor, attenuation factor for this for this beta radiation. In this case, we have to look into the table. Just a moment. So for 800 milligram per squared centimeter, the attenuation coefficient will be equal to mu is equal to 5.8 centimeters squared centimeters per gram. So we will use it. And attenuation factor in this case, as far as the decrease should be by 10%, that means that 90% will go through this layer, and thus the attenuation factor will be equal to 0.9. And thus the D value will be equal to minus logarithm 0.9 divided by mu. So we know mu, and thus we will calculate the D value. So it will be 0.18 in this case gram per squared centimeter. And to calculate this layer in centimeters, the linear thickness, we should divide our d by the density of the material. And in this case, as far as it is water, the density is equal to 1, and thus it will be 0.018 centimeters. So again, it is quite easy. So now we have a bit different task, but related to this one. We have three fluxes, alpha, beta, and monoenergetic electrons. And the thickness, we know the thickness of the material, that is 0.3 millimeters of aluminum screen. And we have to calculate what will be the flux of these particles after the screen. And let's start with alpha particles. We know that the penetration rate of alpha particles in solid materials is equal to few, maybe dozens of microns. In this case, we have a thickness of 300 microns. Thus, all the alpha particles will be stopped by this screen. So the answer that the flux of alpha particles will be equal to 0. All the alpha particles will be stopped. Now about the monoenergetic electrons. Again, the attenuation is rather simple. So it is 1 minus the thickness of our material divided by the maximum range of electrons. And the d value is calculated as a linear thickness multiplied by the density of the material. And yeah, here we have this d maximum. So here we have 1 minus 0.3 millimeters. Let's convert it to centimeters. It will be 10 to minus 1 centimeter. Because we will use the density of the material as per cubic centimeter. And for this, we have already a maximum range. Okay, the maximum range, and let's convert maximum range also to gram per square centimeter, because here we have gram. So we have all the numbers. Let's calculate it. It will be 0.15. So to calculate the flux after the screen, we have multiply this attenuation factor by the attenuation by the initial flux. So it will be equal to so we can write it here. So electrons per seconds. What about the beta particles now? Again, we will use the same equation, and we can take the mu number. In this case, this mu number will be equal to 5 squared centimeter per gram. And thus, attenuation factor for beta particles will be equal to exponent minus 5 centimeter per gram multiplied by this, so it will be 0.003 multiplied by 2.7. So it will be equal to 0.667. And when we will multiply it by 3000, it will be equal to 2001 beta particles per second. Okay, let's go further. The next task is related to radiation safety, and we have a closed radionuclide source of cobalt-60 with known activity, and we have to calculate what is the distance for safe operation of this source for 6 hours a day for the whole year. What is the operating time for safe operation at a distance of ½ meter, and we should calculate the thickness of the LED screen for daily work for 6 hours at a distance of 50 of this ½ meter. So let's I will remind you this simple equation. The dose is equal to activity of our radionuclide divided by the distance from this source, the squared distance. The gamma constant or Kerma constant for our radionuclide, it is we can take from database, from tables, and time for operation. Or we can write it as this. It is not a dose but a dose rate. So yeah, here, but it is an absorbed dose, and to recalculate it to the equivalent dose, we should take into account the difference between the air, and this gamma constant is calculated for the air, and there is a difference between air and biological tissue, and this difference we can assume this difference by this coefficient 109. So let's calculate the dose rate from this source of radiation. Yeah, so we know the K gamma, so it is 80.4, and first we'll try to find the distance. And it is atto grays, so it means 10 to 18 grays, and we should multiply it by the activity, so it is 175 megabecquerels, so 10 to 6 becquerels, divided by r squared and multiplied by 109. Let's multiply all these numbers. So it will be equal to 1.6 10 to 8 divided by r squared. And we remember that for by at least Russian law, this dose rate should be equal, the maximum dose rate is equal to 12 microsievert per hour, and we have to calculate it per second, because here we can see that here it is atto gray squared meter, becquerel is neglected, and it is second minus 1. and it is per hour. And thus we have to convert either by multiplying our number by 3600 seconds, or dividing this number. Let's multiply this, it will be easier. So now we have 5, 7, 6, 10 to minus 5 divided by r squared, and now it is equal to 12 microsievert per hour. And from this we can calculate distance as a square root from 10 to minus 5. It will be 2.2 meters. So the safe distance to operate with this source for 6 hours a day for a whole year is 2.2 meters. So what is now the safe operation time at distance of 0.5 meters? It is, we can calculate it using this equation, for example, or we can do it easier. So we know that the dose rate is inversal to squared distance. Thus, the time also will be the less the distance, the less the time. So, if we know this safe operation time at distance 1, let's say, then this relationship will be equal to this equation. And thus, the safe operation time at another distance we can calculate as a relationship between these two distances. We know the safe operation time 6 hours at distance 2.2 meters, and we want to work at distance 0.5 meters. Oh, sorry. R1 is 2.2, yeah, and R2 is R2 is 0.5. So it will be only 0.31 hours, or if we multiply it by 60, it will be 18.6 minutes. So quite short time to work with this source at very short distance. So if you want to work with the source, you should do it very quickly. Or you can use a LED screen to increase your operation time. And we have to calculate what will be the LED screen for safe operation at this distance of 50 centimeters if we would like to work for 6 hours. So we can see that this coefficient K of for safe operation will be equal to these distances. So it will be the same, but yeah, we should convert it, invert it, sorry, and multiplied by 2. This is the safety coefficient we always use it. So it will be 2.2 divided by 0.5 squared. And we multiplied it by 2, so it will be 38.7. It is how many times we should decrease the flux of our gamma rays to ensure the safe operation. And we should use the special tables. Yeah. They will be in your presentations, but I will check it from my screen. So in this table, we should take this coefficient K, and in this case we can take it as 40, so it is very close to 40, because there is a number for this attenuation coefficient, 40. And the energy of cobalt-60 gamma rays, the maximum energy of gamma rays is equal to 1,300 something. I will check it more precisely. Yeah, 1,333 kilo electron volts, and we will look for this energy in our table, and we will find that it will be equal to roughly 7.3 centimeters. So again, it is not a calculation. We can take it from this table. When we know the coefficient K, you can see here this number, and then we know the energy, and on the cross section of these two numbers, we are finding our number. So we should use around 7 centimeters of lead to ensure the safe operation with this source. So it's not a very thick shielding. Okay, let's go to the next task. Okay, now it is radiation safety of patients during the positron emission tomography or some other maybe procedures. So we have PET diagnostics, and we use this fluorodeoxyglucose, and radioactivity of this sample of this drug is equal to 0.24 gigabecquerel, and we should determine the equivalent dose to the patient if the biological half-life of this compound is equal to 19 minutes. There is a half-life of fluorine as well, and we know the probability of beta plus decay, and we know the energy, maximum energy of these beta particles, and we know that only 50% of the annihilation photons are absorbed by the body, or 50% leave the body. So again, let's start with the definitions. Equivalent dose is equal to the absorbed dose multiplied by the Wien factor. But what particles we have in our case? We have beta plus, so with beta particles, Wien factor is equal to 1, and we know, and we have the annihilation photons, so the Wien factors for gamma radiation also is equal to 1. Thus, we can just write that it is equal to the absorbed dose by the quantity, but of course we remember that we will calculate all the values in sieverts, not in grays. And what is the absorbed dose? It is energy, the absorbed energy divided by the mass. And mass, in our case, it is mass of our patient. And what is the energy? Energy, it is energy of beta particles and energy of the gamma photons that are absorbed in the body. So what is the energy of the beta particles? Energy of the beta particles, it is activity multiplied by the probability of the emitting of these particles and the average energy of the beta particles. So it is 0.5 multiplied by the maximum energy. So it is the average energy of the beta particles. But yeah, we will have, it is not the whole energy that is absorbed by the body, but it is the energy per second. So we can write it like dE dt. Because here it's activity and we don't know the time, and we will see it later. So the same for gamma. What is the energy of gamma rays? So it is again activity, because annihilation photons, they coming from the annihilation of the positrons. Probability of positrons, and we know that the one positron when annihilates with so it is positron with electron, then they produce two photons, gamma, gamma. And thus we have to multiply it by 2. But we know that only 50% of the photons will be absorbed by the body. So we have multiplied it by 0.5. And then we multiplied it by the energy of the photons. So that's it. So we can now rewrite the equation and use not the dose, but the dose rate as this. So it will be these rates of energies, and you can see that we can write these two multipliers and take them off the brackets. And here it will be 0.4 energy of beta maximum plus E gamma. So this multipliers will give us just 1, so we will not use them. And here's the mass. Yeah. Okay. But when we will calculate the dose, it will be the integral by time from initial time to the infinity. Here it will be a p, e beta maximum 0.4, so E gamma divided by mass dt. But in this equation we don't see anything that is depend on time, except only one value, this activity A. A, it is our A0 multiplied by the exponent. But here, lambda is the effective constant rate that is that depends on both biological half-life and the radioactive half-life. And thus we can calculate this dose. We can take all the constants out of our integral. So it is 0.4 A beta maximum plus E gamma divided by the mass of our patient. Oops. And here integral. O infinity exponent means lambda effective t dt. So let's take all this expression as constant. We will calculate it later. So the d will be equal from this to our constant. Then it is 1 divided by lambda effective. And then it is minus exponent minus lambda effective t. And here the borders for limits for integration will be this, because we invert our minus and we change our integration limits, and thus this will give us just 1. So we can write that the whole dose will be equal to our initial activity, probability of the beta plus particles, energy average of the beta plus particles, energy of gamma quant, and we divide it by the effective constant rate and the mass of the patient. So it is the almost full equation, but we should take into account that lambda effective, it is lambda biological plus lambda radioactive, and thus when we convert it and we will use the half-lives, it will give us finally the d value equal to A0 P 0.4 E beta maximum E gamma logarithm 2 mass of our patient, and here it will be so sum of half-lives bu plus radioactive, and here will be the product. So now we have all the numbers. A, it is 0.24 gigabecquerels, P 0.97, energy maximum 0.635 mega electron volts, E gamma 511 kilo electron volts. All these numbers we have to convert to joules. And half-lives are given in minutes, and we have to convert them in seconds. So if we will calculate all these numbers, so it will be 1.3 millisievert. So you can check it by yourself. So there is a question, one moment. Okay, so it was the most important tasks that we solved through the course of radioactivity, and it was our last lesson, last seminar in this year. But I will see you next week for our last lecture. Okay, that is all for today. Goodbye.